Good morning, everybody. So this is the last tutorial part of our Isolde sessions. Today I wanted to go a little bit into flexible fitting approaches using Isolde, and for this I generated a new folder. So if you start up ChimeraX, you can go to the cloud, and under lab data and tutorials, Isolde session 3, you will find a bunch of models and the map. And I would like to ask you to load basically model ABC and chain, sorry, my bad, the first model, which is the one we've been working with all the time, but I deleted one piece. And the second one is chain Z, and you will see now that I moved it in a different position, and it's the second model that we actually have to load. If we open the corresponding map, we will see that this domain is clearly out of place. So how can we now basically do a fitting? So there's different ways to it. I think if you already have the perfect fold and you just need to do the fitting like in this scenario, what is sufficient is a rigid body approach. So how do we do this? So one of the steps would be to make the task a bit easier is to make a smoothened map of this high resolution map. Why is this the case? Because this is such high resolution that sometimes it's actually really challenging to see secondary structure elements. How do we do this? We say volume Gaussian, and we select the map ID, which is 3, and we apply a B factor of, let's say, plus 150. And if we do this, we will get a second map that looks like this, and I think we can all agree that it's much easier to see helices and sheets in a lower resolution map or a smoothened map. So to now move the domain, we can select this domain. Since this is an entire model, we can just say, okay, select this domain, and the domain is here ID number 2. And now it's selected, and under the right mouse options, you find move domain and you find rotate domain. And with these two domain commands, you can essentially start moving around. So that's already fairly close to where it should be. I think what can be really used nicely, if I move it away, is a very long helix that runs from the top here almost to the bottom of the protein. So this is the other side. Here's the bottom, here's the top. It's a small turn, connects it to another helix. If we look at the model, we find this long helix from here to here, and we can go and hover over it, and its residue number is 217 to 258. So if I say select 200, model number 2, and the residue range 217 to 258, I was obviously wrong. It's 2197. Yes, that's better. And okay, because I got the linker wrong, my bad. So we just select this helix, which is very long, and we just go from 197 to 219, and I say color selection red, so clear. So we now have it colored, and we know approximately where this helix should go. So now we have a marker point. So if we now select the entire domain and move it with the rigid body moving commands on the right mouse options, we can start playing around with this and try to get this helix very close to its density. You see that the helix isn't yet fitting very well, so we need some rotations as well. Something like that, maybe. Getting closer. That is already fairly close, something like that. Maybe a bit here and move it in. So that's basically already a very good approximation of what needs to happen here. To make this even better, there's a function in ChimeraX to do this, and for this you type fit, and you type the model ID, which is number 2, in the ID of the map that you want to fit against, and this will fit in. This is 4. If we do this, it will do the fitting. In this case, we can also use the high resolution map, which is 3, and you see there's a slight correction of the model position, which is due to the higher resolution of the other map, so we have more information and can place it more accurately. Okay, that is basically an approach to do rigid body fitting. But that's not what I wanted to deal with mainly in this tutorial, and that is how to actually deal with this situation if we have the situation that we need to move things dynamically. Okay, to kind of fake this situation, I would just move the domain away from its density and I will start Isolde. Like this. Now that we are having Isolde up and running, we can choose the model that we actually want to manipulate, which is here this second one. And we want to associate it with the map. In this case, I would like to associate it with both maps. So I click on both and 2 times I click on go. And on the map settings, I change the preference of view on both of them. And if I'm doing this and change the threshold, I get both maps displayed in Isolde, and I can use both maps to do the fitting. In this case, I would like to start off with the smoothened map because it's a bit easier to see the secondary structure elements. I will increase the spotlight radius a little bit, and now we go into dealing with the model for Isolde. As you know, this model has water molecules in it. I don't like that for now. Typically you don't face them anyway, I think, unless you get very high resolution. You're not building any water molecules. So with select tilde protein command, I can select everything that is not a protein, and with delete selection, the water is gone. First thing. Second thing is, if I were to now start a simulation here, I need to add hydrogens to the model. So I type the add H command, and that will add all the hydrogens. If you don't do this, Isolde will complain and will ask you to do the job for you. Second thing. Third thing is we just run a simulation of the entire thing. So first I select clear all the selections with this command, so basically unselecting everything. And now there's 2 options to select things in this model. So one of them would be control mouse. Control mouse allows you to draw a box basically and select whatever you want to do. You can select pieces, and that is quite useful for flexible fitting approaches. If you want to have much more control over the process, you can of course also write select, for example, model number 2. In this case, you can see also the ID here. You can type 2.2 or just 2 because there is no model 2.1 or 2.3, so 2 just works as well. And you provide the chain ID and the residue range 1 to 100, and you get this selection very specifically. So what I wanted to show you now is if you run a simulation without having a map, that is actually a disaster. Because there is nothing to fit the model against, and it will just fall apart. And that's what you can see now if I start the simulation. So parts here of this model are being attracted by the map that is in this area. I will briefly pause the simulation and re-enter the spotlight radius number, because whenever you start the simulation, the selection of the spotlight will jump back to the residue selection, and since there is no map around, the map is not being displayed in the neighborhood. But we can actually recall this by remeasuring or re-entering the spotlight number here, and you will see here it comes again. So resuming the simulation, you will now see that parts of the model are being attracted by this density, and it's basically destroying your model, which is not what you want, right? So how can we prevent this from happening? So first of all, I click on the stop button, and for this we basically have restraints, and these restraints are being applied to maintain the fold of the domain. So there's 2 types of restraints. The first one is to address distances in the model, so that Isolde basically knows what is the distance between certain residues. For this we type Isolde restrain distances, just as we used it last time. We support this command with the model ID and the chain, and if we do this and press enter, you will see that now distance restraints are being applied. We can change the force that is being used in these restraints by adding a kappa value, and here I will use a ridiculously high number of 200. If you go to the web page of Isolde, you can actually find these commands as well, and also what kappa does and what happens if you use very low values, etc. But this is for very strong restraints, so that will try to keep the domain together as good as possible. Then there is another command which I will now just use to have a better view on it, and this is Isolde adjust distances. Same model and same chain, and say display threshold 1. That is an H missing in the command. If you do this, the distance restraints are still there, they're just not being displayed anymore. And that sometimes helps when you do the dynamic fitting, that you know, okay, they're there and they're acting on it, but you don't see them, so they're not obscuring the view. But whenever something passes the threshold of 1, these restraints will actually reappear, but now they don't, because this is just an static scenario. The second type of restraints are actually torsions. For this, I will just delete the kappa part of this command and replace distances by torsions. When I'm doing this, you see this little circle surrounding the sidechain. So now Isolde also knows what is the rotomer conformation of each and every residue in this model. Equipped with this, we can basically again select everything, and we can fire up the simulation again. By doing so, again, this map will very likely disappear now. It does. To call it back, I will pause the simulation and re-enter this value here, which will bring back the map in a second. This is much faster if you pause the simulation. When it is running and you try to do that, that could easily crash your computer if it is not a well-performing one. Resume the simulation and you will see now nothing is being distorted. You can sometimes see the torsion restraints and the distance restraints actually acting on the model here, keeping things together, although they want to really move. But the restraints are so strong that they don't allow things to fall apart. So that's very good. That's one part of the solution. Second part is we do what we've been doing before. So the atoms and stick representation is rather difficult to see secondary structure elements in this one here, right? So even if I go closer, seeing a helix even without the selection is rather difficult. So we changed the view into this ribbon diagram, so to speak, and that makes it much easier. And we can also change colors again. So I go back in the commands here, down in the command line, by just pressing the up arrow. We can basically go back to these commands and call them back. We can also go to this little drop down menu and you see all the commands that you've been using throughout your session. Now I select this helix again. I say select or color selection red, and we have again a red helix. So that's this part. The further we're moving away from where we are supposed to be, the less we see on the map. So now we want to do this flexible fitting. Keep in mind we have the domain running, or the simulation running all the time. This red helix here belongs into this place. This is the corresponding density. So there's now two ways how we can do this. The first way would be to select everything with the mouse, control mouse option. We can also select everything by selecting just model 3 and model 2 and chain Z. And if we have done that, we can use the tuck command, which is down here. It says tuck the currently selected atoms. By clicking that and then using the right mouse button, I can actually start moving that domain within the simulation. And notice that the domain stays together because of the restraints. You don't see them acting now so much, and that is because we are using the representation of the carton. So I'm starting to move that to where it actually belongs, and then I stop the motion, and we see that's not quite right yet. So we can also just select a bit and the piece of the top and move that a little bit closer to where it should be sitting. Oops. There was obviously a problem with a clash occurring. That's typically not happening. Yeah, okay, this is what it is. So I just clicked on stop. It goes back to the original coordinates. I call back the helix color by doing this kind of selection. Select everything and rerun the simulation. Go to pause, change spotlight radius. This brings back the map. Resume, select everything and try to tuck. And now you can actually see how the model is being moved slowly into its corresponding density, hoping that we will find the right spot. And at some point the model should start basically finding its way into this map more or less automatically. So I'm not doing anything anymore at the moment. So this is now just a flexible fitting approach. So this is what Isolde is doing. Maybe it needs a little bit more of tugging. And that was a movement that basically puts it into the density where it belongs. And that's the task accomplished. So now I will change the view back to this one. You can see here now that the helix is actually perfectly fitting where it belongs. And in such manner we can actually move domain pieces and keep them together. What I will now show you again is, now that you know how to do it together with the distance restraints being displayed, because that is a bit obscuring the view. To do this, I will use the command for adjust distances and change the threshold back to 0. And in the preset options we had chosen to choose the carton, but we can show instead hide this view and bring back essentially the atom view. And we can do this for all the domain. So here it is. Here you now see the restraints acting basically on this model, and you see how strongly they are pulling to keep things together and to keep things happy. And this is mostly where you see them acting very strongly. You see that where you have secondary structure elements in which the density is not super strong. So the information of the map is just not extremely good. And if this is the case, then you need more of the restraints to compensate for the weaker map. Okay, having said this, what I noticed here is that few areas are actually having some problems during the motion. Some of the areas actually change their rotamers, and this means we need to kind of deal with this. And there is a nice way of doing this, and I will show you how to, because we actually do have 3 other copies of the same domain in the same structure. So what I'm doing here is I stop the selection. I will now repeat the same thing, and I will do the same thing only with the side chains being shown for the entire domain. I will start the run, and you can actually see how some residues are flipping, although we have these restraints applied. So when you do this kind of thing, there's 2 options to recover from this. We tuck the domain and we essentially okay, now I didn't select everything properly, obviously. Now we have it. I will briefly pause, bring back the map. Continue the simulation, and start tugging. So this is in a rapid way essentially the flexible fitting approach, now with side chains being displayed. So now I will actually save this new position because I know it's correct. And what we can do next is to restore essentially everything in terms of the rotations and the folds. So the backbone geometry and rotomers. We stop the simulation, and now there's two ways of doing that. I think one of the best ways would be either taking the information from one of the other chains, or alternatively we just open the same model again. We don't need it for anything else but taking the structural information. I'm not displaying it here, but I will now use the restrain command again by saying Isolde restrain the distances in my model number 2.2 in chain Z, and take as template atoms the model that I just opened 3, also chain Z. By doing this, maybe even strong restraints, the restraints will be taken from the other model, which did not undergo the motion. Same can be done with the side chains, torsions. Then we have to exchange here for residues, and kappa 200 we change for angle range 180. And then we have also the side chain information coming from the other structure number 3. So now we can basically select this model with the chain number Z. And if we start the simulation, what will happen is it will apply these restraints coming from the intact domain. And what you can see now is that the areas that were problematic before are all fixed at once. It's pretty fast, so I show it again by restarting the simulation. You can, for example, focus on this area here, which in the beginning is now a Hamburg outlier. We see also, maybe I can Isolde adjust distances into display threshold 1. Isolde. So now you see it a bit better, that we actually have a couple of rotomer problems that we caused. For example, here, this one is a rotomer error, here's a rotomer error. We have some Hammerhandram problems that were introduced through this motion. So nothing very spectacular. The fit is great, but in some areas could be a little bit better though. But what we want to really do is to restore the conformation. To do this, what we can do is, as I said, just apply the restraints coming from the other domain. And if I now select this domain and run it, you see that these problems are being fixed instantaneously, just by taking the restraints coming from the other model. Done. And it's also sitting much better in its density. You see this motion down here. Here you go. That's it. Okay. Alternatively, we can also try to take the information coming from another domain. And if you want to do this, we can, for example, go back to this torsion restraint command, and we don't use as a template 3, but we could just use, for example, ABC, which is model number 1, and we say chain A. So we take whatever is coming here, I guess that is, no, the blue one is chain A, yes. And we do the same for the distances. We change here to 1, and we change to chain A, and we say kappa is 200. Now here are the restraints, and if we now select this model, I now use control mouse to select everything and rerun it. It should just be fixed the same way, but keep in mind that we're now applying whatever is in this model number A, and if it looks different, then also the new model here will be looking different to some extent. This depends on how good the map is. because whenever you apply these restraints, it's like a fight between the map and the restraints. In default settings, a good map is always stronger than the restraints themselves. Okay, but looking at this in the cartoon view, we basically have solved this problem. And that's what we wanted to do, and this is basically the end of this task. With this, I would like to stop the simulation and go a little bit into a different chapter of what people were interested in. There's two things I would like to show before we come to an end. So first of all, I will close this additional domain, and I will change back to the presets here. So one thing is, actually, now that we have moved the domain into its place, we also want to have it as a part of this complex, right? So we know that we have chain IDs A, B, C, and this is chain ID Z, but we want to have it in D. And for this, there is actually a very simple command to do this. The command, I have it in my command list that I send around in one of the earlier emails. 1 second. Of course, now I'm not finding it. Here it is. Set attribute is the command. If you just type that and you say, okay, I want to change in 2.2 chain Z to chain ID number D, this is all you need to do. And if you hover over it, you will see that this chain is now 2.2 and D. So how now to make a complex? It's also very straightforward and simple. You have two IDs, 1 and 2. You can select them both. You can select just one or the other, but we want to select both 1, 2. And then you can ask Isolde to say Isolde model building merge models, and that's it essentially. Once you've done this, you can close model 2 and you will see that it has been merged. It's now in here and the chain ID is number D. And if you save this as a new file, ABCD PDB, you basically have made a complex. I close this and reopen ABCD, and here we go. Coming to the last part basically of this tutorial, people were interested in how to change actually residue numbers, and that can be a bit more tricky. Actually, I haven't figured out how to do that easily in Isolde, so for this I will basically change the software type. I close Isolde and I will fire up Coot for Windows. So this is WinCoot, and you can download this from the web. So this is, I guess by now there must be version 09.5 or something. I haven't used it much in the last 2 years, but it's still a very convenient way to change residue numbers and also chain IDs. Be aware that the two formats, PDB and CIF, are not always easily interchangeable, and this can be especially a problem when you decide to give chain IDs 2 letter codes. So for example, if your chain IDs are not ABCD but AA, BB, CC, DD, and you want to save this as a PDB file, it would not work, and it will give you a corrupt PDB file because the PDB does not support 2 columns for the chain ID. Unfortunately, for large complexes like the type 3 secretion system, or as we did it also in type 7, that can be then a very delicate task, because you cannot easily cycle between the programs, because some of them, they don't properly write CIF files yet. So we have not yet reached an agreement that people only use CIF format, which is probably, hopefully, happening in the near future. Okay, so in Coot, once you have this up and running, you don't need the latest version for that. So there's a basic function you will find in all of the Coots. There is a Coot also for Macs, for Linux systems, and for Windows. So there's something for everyone. You just go to Open Coordinates, and we go to the folder where I just saved this model under Tutorials, Isolde, Session 3, ABCD. Okay, here's the model. This is how it looks like in Coot. In fact, you can also open the map here, File, Open Map. So maybe we do a little bit of Coot in here as well, because this is one of the standard model building softwares, and you load the map. With the mouse wheel, you can actually change the threshold of the map, and this is how the map could look like in default representation in Coot. Okay, Under Display Manager, we can basically see the map and the model, and we can say, okay, I don't want to display the map here, and I don't want to right now. Under Draw, Calculate and Edit are the most important features that we're going to need. For example, we can go to Draw and then go to Atom. That gives you basically an Atom viewer window. And first of all, you get displayed the 4 chain IDs, and I would like to go to chain, let's say, D, and you can select the residue, and by double clicking you will be sent to this residue in the structure. Here it is, it's histidine residue, and it tells you it's chain A and it's position number 2, it's histidine in chain D. Fine. So now how to address chain IDs and residue numbering. So one way of doing that, for example, is by the edit function, and you can say change chain IDs. And if you do this, you can, for example, say I would like to change chain ID D, and I would like to change the whole chain to Z. By doing so, your task is basically fulfilled, and that's it. If you then go to File and Save Coordinates, you have the same thing, but this chain ID has been changed to Z. I change it back to D, and we're back in D. The same way, you can also change residues by renumbering residues here, and you can choose the domain ID, which is D. You can choose a range, I say the entire domain from N to C terminus, but you can also provide the residue range, and you can say you can apply an offset. So I would now say, okay, this is all wrong. It starts not with histidine in position 2, but in position 12. So I apply an offset of +10. By doing so, this residue is now 12, and it starts from 12, whereas all the other ones start from 2. If I save this file, now I need to go to the folder, so you have it also in there. Sorry, that takes a second. Session number 3, ABCD, res number adjusted PDB. Then you have this new file, and I will just cycle it back to ChimeraX. And if we do this, you will now see here's a bit of a problem. This typically happens because all the programs write secondary structure elements in a different way, and when Coot writes it, and ChimeraX doesn't really know what to do with this part of the PDB file. If you save this and reopen it, the problem will be solved. But what you also can see here is now you have ABCD. If we go to chain D, you see that this is actually causing the issue here now. But when we go to the end terminus, you will see, hopefully, that when I hover over it, yes, that the starting residue is now residue number 12 instead of residue number 2. And with this, I think this is the end of this tutorial session. If you have any further demands or specific questions, don't hesitate to just write an email, ask some questions. I think should be available beyond my time here in Thomas's lab to answer some model building related questions. I don't know for how much longer my email will be alive and active, so but I of course can also provide you with my private email, and you send just the questions that may arise in the process of dealing with such problems to my email, and I will try to reply as fast as possible. With this, thank you very much for your attention, and I enjoy the model building, which nowadays you anyway going to do with AlphaFold. With this, have a good one and see you later.